Okay, so now I'm recording this Zoom so that I can share my screen and we can look at some graphs, because what I did want to do was to go back and look at the graph of the function and then the graph of the derivative. First of all, I did want to go back and fix what I had done, though, because remember, it was the 6, and in fact, I wanted it to be a 3 instead of the 6, because if you go back and redo the calculation, you'll find that that gives you the derivative being 0 at x equals plus or minus 1, not root 2. Why? It's just easier to see it on the graph, you know, because it goes through the point, right? Where there's a... Okay, so, but what does this mean? What does this mean in terms of graphing? Okay, so let's think about it for a few minutes, right? And we'll think about what it means graphically speaking, right? If I'm thinking about the derivative as a graph, right? Or then I'll think, and I'm going to think about the derivative as a graph, but I'm also going to think about the original graph, okay? Now, if I've got an original graph, f of x, right? And it's increasing, right? That kind of means it's going up, right? And going up like this. So if I look at the slope when it's increasing, that slope is going to be positive, right? This is a positive slope line. So then my derivative is going to be greater than 0, right? Now the same thing is going to have, the opposite thing rather, is going to happen when I'm decreasing. If my function is decreasing, the derivative has a negative slope. The slope is negative, so the derivative has a negative value. So what I have here is the derivative has a positive value, negative, the derivative has a negative value. And if it's neither increasing nor decreasing, then my derivative is going to be 0. So we talked about that. So I'm going to put horizontal tangent here. And that gives me that the derivative is 0. Now that horizontal tangent, as we saw last week when we did, we had a little bit of discussion about that on the worksheet, it can happen in a couple of ways. It can happen at the top of a hump, and it can happen at the bottom of a hump. It can also kind of happen in between if the function gets really flat, okay? But for the most part, we're gonna mostly see these, especially say this week, okay? Later on, we'll talk about this point of inflection business when we're dealing with derivatives more when we're looking at the heck is the word I'm going to be, like the algebraic form, like when we're actually working with the formula rather than just looking at the graph. Primarily, what we're going to talk about today is sort of looking at the graph and figuring out what's going on with the graph. So with this in mind, let's take a look at the graph of this function and the graph of its derivative, and just let's see how that looks in terms of what we have calculated. Okay, so here's the function. Maybe I can go in a little bit here. Maybe I don't want to go in too much. Okay, good enough. Okay, so you can at least still see here. So remember when we found out we did, okay, where is the horizontal tangent? When I fixed the number, it turned out to be -1 and 1, right? So here you can see the top of the hump and the bottom of the hump is indeed -1 and 1. You can imagine that that is a horizontal tangent there. On the left-hand side here, my function is increasing, right? And then it decreases from -1 to 1, and then it increases again, right? So if my function is increasing, that means that my derivative has to be above the axis. And if my function is decreasing, it means that my derivative has to be below the axis because I've got positive values and negative values, okay? So, and I want to think about, okay, how big are those values going to be? I mean, we can kind of eyeball this. In the middle, it's probably like the steepest in the middle, and maybe it looks like it's around -3. 1, 2, 3. Yeah, looks like a slope of -3, maybe in the middle there where it's steepest. The best you can do with these, if you're just looking at it graphically, is kind of going to be to eyeball it. But we can do a little bit better than that because we actually figured out in the last video, figured out slightly, but I fixed the number. So this is actually over here. Come on, guys, come on. There we go. That is the actual derivative, 3x squared minus 3. Now let me zoom a little bit out so we can see that a little better. Oh, come on. I'm having some issues here with my old computer and my mouse. Okay, there we go. Ha! It did look like -3. It goes right through there. Imagine that. But we actually saw it when we looked here. If we looked close enough, we could tell. So the green one is the derivative. And the thing I wanted to try to make a point, because this is something that gets confusing at first. The function is increasing, right? All the way up. So the red one is increasing all the way up to -1. That means that the function values are positive. But actually, if you think about what is the slope doing, the slope is much bigger down here than it is over here. And you can see that. So the slope was pretty big over here. And as I get closer and closer to the point of x equals 1, the slope of this graph gets smaller and smaller. So it goes smaller and smaller and smaller to 0. And now here we have something that is, the slope is 0. The slope goes lowest it is, most negative is going to be -3. And then the slope is going to increase back to 0. And then we can see that right nicely here, how it does that. And now it's going to cross the axis because the function itself has a horizontal tangent there. So the derivative crosses the axis and now it's going up. Desmos has drawn these points here because it automatically puts in the points where things intersect. But the points where the two functions intersect are not really something that we care about very much. What I'm interested in is seeing that you can tell from something like, okay, come on, this, you can tell it's going to go through 0 there, it's going to go through 0 there, this is going to be positive, negative, positive. Basically, like that kind of more basic idea. It doesn't have to be exact, whether it's going to -3 or -4 or whatever, it doesn't have to be exact, but just that it's clear where it's positive and negative and that sort of thing. All right, so that is that one. I have another example here that I wanted to kind of look at. I have some problems with this mouse here. Okay, this example here, again, you can see what the formula is. It's just sort of a formula I made up. I do not want you to do this calculation to find the derivative of this thing because that would be very onerous, right? But here is sort of an interesting thing. The function actually goes through the point 0 and the point at 2 and the point at 5 are both zeros of the function. But in fact, you can see they're also the bottom of the hump. So the derivative, just by looking at this picture, the derivative is going to go through 0 at 2, and it's going to go through 0 at 5, and then it's going to go through 0 here at the top of this hump, which top of this hump looks like it is halfway in between there. So I'm going to say it's 3.5, right? So and then it's above, below, above, below, above. Okay, so let me just keep this in your mind. Well, maybe you can see it here. I'll draw it and then I'll make my drawing bigger when I stop the screen share. So what did we say? We had the top and the bottoms of the humps here. 1, 2, 3, 4, 5, 6. So it was at 2, at 5, and at 3.5, right? Those were the maximums and minimums, local max and local min of the function, is what they're called, but we can just call them top and bottom of the hump right now. Okay, so here my function is decreasing, which means I have to be down here. And then here from 2 to 3.5, I'm increasing. So it's increasing, but this is the same kind of idea as we saw in the previous example. Like in the middle, it might be like not even 3, 2, 2.5, something like this. It doesn't really matter. So we can just make it, say, go to 2. I just want to see that it's on the right side of the thing. Here, fix that. That's not very pretty. There we go. And then from 3.5 to 5, again, it's decreasing. So it's going to be down here. But it's going to go from 0, I mean the derivative is going to go from 0 to 0, and it's going to hit like a minimum of whatever, -2-ish, -2.5, I don't know. And then here, it's going to be increasing again. So my derivative looks something like that. And all I really want to see, let me get rid of this screen share so it gets bigger. All I really want to see is that you have the features of the graph. So whether this goes up to 2 or 3 or 1, doesn't matter so much, but I need to see that the graph goes up and goes down. So that is the basics of drawing the function's derivative from the function itself.